Today, 3I/Atlas, only the third object ever seen from interstellar space, has finally arrived, moving faster than anything we've tracked in our solar system. In less than 24 hours, at its closest pass to the Sun, we might learn if it's natural or something engineered. But at the critical moment, Atlas will be hidden from Earth behind the solar glare, taking its final exam where no one can watch. Could this be the first real test of whether we're alone or just a cosmic trick of nature? It all started with a single alert that changed everything. On the night of July 1st, 2025, the Atlas telescope in Chile swept its field as usual, searching for anything out of place among the stars. Its software compared fresh images to the night before, hunting for movement that didn't match the catalog. That's when the system caught it. A point of light not found in any database, moving faster than the usual suspects. The automated alert triggered instantly, flagging the object for urgent review. Within hours, the Atlas team checked the data by hand, ruling out camera glitches, satellites, or cosmic rays. The coordinates, timestamp, and brightness all held up under scrutiny. Standard protocol kicked in. The team cross-checked the Minor Planet Center's records and ran the object through their orbit calculators. Nothing matched. The motion was too quick, the path too strange for a local asteroid. Satisfied it was real, they sent a formal report to the Minor Planet Center before sunrise, including every detail: position, trajectory, and the exact time of detection. By the end of the day, a Minor Planet electronic circular carried the news to astronomers worldwide, a new discovery now awaiting confirmation. The next step happened fast. With the initial data in hand, orbit solvers ran the numbers. The trajectory wasn't just odd, it was unmistakably hyperbolic, a path that would never loop back to the Sun. This meant only one thing: the object wasn't from here. It had come from beyond the solar system, joining a list that, until now, had only two names. The designation arrived almost immediately: 3I, Third Interstellar. In a matter of hours, a routine survey had ended the object's anonymity, and the world's telescopes were suddenly aimed at something not just new, but fundamentally alien to our neighborhood. The numbers behind 3I/Atlas challenge expectations at every turn. Early measurements placed its diameter at up to 5 kilometers, dwarfing both Oumuamua and Borisov. For context, Oumuamua was estimated at a few hundred meters long, while Borisov measured about a kilometer across. Atlas is, by any standard, a giant among interstellar visitors. Size alone would have drawn attention, but its speed is what truly set it apart. Calculations showed the object racing toward the inner solar system at a velocity that eclipsed all previous records for natural interstellar bodies. At perihelion, it would reach nearly 68 kilometers per second relative to the Sun, fast enough to escape the solar system without ever being captured by gravity. The trajectory, though, is where the statistical oddities begin to stack up. Instead of plunging in from a random angle, Atlas entered the solar system almost perfectly along the ecliptic, the thin, flat plane where all the major planets orbit. Its inclination is just 5 degrees off this disk, and it's traveling retrograde, meaning it moves opposite to the planet's direction. This isn't just rare, it's almost unheard of. Most interstellar objects approach from above or below, crossing the planetary plane at steep angles. The odds of a random interstellar object threading the solar system so precisely are vanishingly small, especially at this scale and speed. This alignment isn't just a curiosity, it brings Atlas close to Mars, Venus, Earth, and Jupiter in sequence, as if it's following the planet's own path. Astronomers and statisticians alike have struggled to find a natural explanation for this level of coincidence. While some argue that cosmic randomness occasionally produces strange alignments, others point out that this degree of planar matching, combined with the object's size and speed, makes Atlas an outlier in every sense. The numerical improbability isn't just a matter of statistics, it's a source of growing suspicion, fueling debates about what or who might have sent it our way. Spectrographs and polarimeters turned toward 3I/Atlas as soon as its interstellar nature was confirmed, searching for clues in its chemistry. The first surprise came from the coma, where carbon dioxide dominated the gas signature. Instruments like SphereX and ground-based telescopes picked up unusually strong carbon dioxide emission, far exceeding what is typical for comets in this part of the solar system. Water vapor was present, but the ratio skewed heavily toward carbon dioxide, an outlier compared to most Oort cloud or Jupiter family comets, which are usually rich in water ice. The implication is that Atlas formed in a region of deep cold, or under conditions where carbon dioxide could freeze and persist, pointing to a birthplace far from any sun-like star. The anomalies did not stop there. As the coma thickened, observers using the Very Large Telescope and Gemini South caught emission lines from vaporized nickel. What drew attention was not just the presence of nickel, but the absence of iron. In solar system comets, nickel and iron typically sublimate together, released from dust grains as they heat up. Here, nickel appeared first and at much higher levels, while iron was almost undetectable in early spectra. This pattern held across multiple independent datasets, including follow-ups from the James Webb Space Telescope. Laboratory studies suggest that only specific interstellar processes, or perhaps unusual surface chemistry, could separate these metals to such a degree. Some researchers pointed to photolysis of nickel-rich compounds as a possible explanation, but the selectivity remains hard to match with standard comet models. Polarimetry added a third layer of strangeness. Light scattering off Atlas's coma produced an extreme negative polarization signal, measured consistently by the Very Large Telescope, Nordic Optical Telescope, and Rosen Observatory. This effect is rare among comets, but more common in the dark, compact grains found on trans-Neptunian objects. The data suggest a surface or coma dust population with unfamiliar structure, possibly non-porous grains or even metallic coatings. Mainstream interpretations lean toward exotic but natural interstellar dust, yet the measurements resist easy classification. Taken together, these findings set Atlas apart from every comet previously studied. The carbon dioxide dominance, the nickel without iron sequence, and the polarization profile all point to a chemistry and grain structure that does not fit established families. Each anomaly has plausible, if rare, natural explanations, but the combination is unprecedented. For those watching the object's approach to the Sun, these lab results set the stage for bigger questions about origin, formation, and, for some, the possibility of design. Time series imaging of 3I/Atlas captured a sequence that unsettled expectations. In the days after its discovery, astronomers watched as the comet developed an anti-tail, a narrow, faint wedge of dust and gas pointing toward the Sun, not away from it. This reverse structure contradicted the usual behavior of cometary tails, which are shaped by solar radiation and wind, always streaming outward. Instead, Atlas seemed to trail a banner along its orbital path, as if dust grains were lingering behind, resisting the Sun's push. The anti-tail persisted for days, sharp and distinct in exposures from observatories across both hemispheres. Its orientation shifted with the comet's position, but the anomaly remained. The most prominent feature was not the expected luminous tail, but a reversed filament, visible even as the comet's activity fluctuated. Astronomers compared these images to models of dust grain motion and solar pressure, searching for an explanation. Some cited the geometry of Earth's vantage point, noting that when our planet crosses a comet's orbital plane, large, slow-moving particles can create the illusion of an anti-tail. Others pointed out that Atlas's anti-tail was unusually pronounced and appeared just as the comet's outgassing rate spiked. The timing suggested more than a simple trick of perspective. The debate intensified as the anti-tail's brightness and sharpness shifted night by night, tracked in stacked exposures and time-lapse sequences. As Atlas drew closer to the Sun, the anti-tail faded. In its place, a classic cometary tail emerged, broad, luminous, and streaming directly away from the Sun, composed of fine dust and gas driven by solar heating. The transition was abrupt, documented in nightly images from the Gemini South Telescope and amateur astronomers worldwide. The new tail grew rapidly, soon dwarfing the earlier anti-tail. For some, this marked a natural progression, a comet awakening as it neared the inner solar system, shedding outer layers under rising temperatures. For others, the sharp morphological shift hinted at something less routine, perhaps even controlled activity. Throughout, the comet's shifting tails became a magnet for speculation. Time-lapse animations circulated among researchers and online, fueling arguments about dust dynamics and comet behavior. The visual record offered no easy answers, but it did underscore one thing: Atlas refused to conform, its evolving tail structures adding to the growing list of anomalies and inviting fresh scrutiny from those concerned with planetary security. Avi Loeb, a Harvard astrophysicist known for challenging mainstream assumptions, has become the most persistent public voice warning that 3I/Atlas might not be just a comet. He points to the uncomfortable reality facing astronomers and policymakers alike. The decisive moment, perihelion on 29 October 2025, will unfold where Earth cannot watch. As Atlas swings to its closest approach to the Sun, 1.36 astronomical units, just inside Mars's orbit, our planet will be on the far side, blinded by the solar glare. No ground-based telescope can track the event in real time. The object's final exam happens in a cosmic blind spot, hidden from direct view during the hours when it will experience maximum stress and heating. For Loeb, this geometry isn't just frustrating, it's a vulnerability. He calls it the Trojan horse problem. The question is simple but unsettling. Could an object that looks like a comet be something else entirely, carrying unknown cargo or technology beneath an icy shell? Loeb argues that, even if the odds are low, the consequences are too large to ignore. He frames Atlas as a classic black swan event, an outlier that, if mishandled, could have civilization-scale impact. His message to governments is blunt: do not assume that a comet-like appearance means safety. The path, the timing, the chemistry, and now the observational blind spot all add up to a scenario that demands more than routine scientific curiosity. Loeb's warnings have landed in policy circles already primed by earlier interstellar visitors. Unlike Oumuamua, which passed quickly and quietly, and Borisov, which behaved like a textbook comet, Atlas combines statistical oddity with a level of planetary alignment that is hard to write off as mere chance. The object's trajectory threads the inner solar system, passing near Mars in October 2025, Venus in early November, Earth's orbital neighborhood in December, and Jupiter in March 2026. Loeb and his collaborators argue that such a sequence, so neatly in line with the ecliptic, is more than a curiosity. They urge that the possibility of deployment events, the release of probes, signals, or even artificial objects should be treated as a real, if remote, risk. The debate has spilled from scientific journals into closed-door government briefings and public policy forums. Some national security analysts now reference Loeb's black swan framing in their risk assessments. The perihelion blind spot in particular has become a focal point. With no direct line of sight, any sudden change, fragmentation, course alteration, or unexplained emissions could go undetected until the object emerges from behind the sun. The fear is not just what Atlas is, but what it could do when no one is watching. This climate of uncertainty has prompted a surge in contingency planning. Space agencies are coordinating indirect monitoring campaigns, using spacecraft positioned near Mars, Venus, and Jupiter to catch whatever evidence they can. Instruments sensitive to radio, infrared, and charged particles are primed for any anomaly. Meanwhile, Loeb's Galileo project is preparing to scan Earth's upper atmosphere for signs of anything entering from space in the weeks after perihelion. The global scientific community is mobilized, but the existential question remains unresolved. Is Atlas a cosmic relic or a messenger with a hidden agenda? In the absence of direct observation, the stakes have never felt higher. Mission teams have spent months preparing for the aftermath of Atlas's hidden moment. With direct observation blocked during perihelion, the focus turns to a coordinated campaign of spacecraft, telescopes, and atmospheric sensors, each positioned to catch whatever the sun's glare might conceal. Scientists at the European Space Agency have scheduled the JUICE probe, now en route to Jupiter, to scan for changes in the comet's coma and tail as Atlas swings past Mars, then Venus, then approaches Earth's orbital neighborhood in December. NASA's Mars Reconnaissance Orbiter and MAVEN will monitor for dust or gas signatures that could drift across Mars's thin atmosphere, hunting for any hint of fragments or outgassing mist during the solar conjunction. Closer to home, the Hubble Space Telescope and the James Webb Space Telescope are preparing for a series of post-perihelion observations. Webb's NIR-SPEC instrument is set to take detailed spectra in December, searching for confirmation of the unusual carbon dioxide dominance, the nickel vapor, and the possible presence of complex organics. Hubble will track the nucleus and coma for sudden changes in brightness, shape, or composition, signs of breakup, survival, or even something less expected. Attention isn't limited to the inner solar system. As Atlas heads toward Jupiter in March 2026, NASA's Juno spacecraft will listen for radio signals and scan for any anomalous emissions. The goal? To catch anything that might hint at artificial activity, or simply to record the chemistry of a truly alien object as it passes within 0.36 AU of the giant planet. ESA's JUICE will continue to gather high-resolution images and spectra, adding to the library of data that could redefine what's known about interstellar chemistry. Meanwhile, the Galileo project ramps up its own efforts. Led by Avi Loeb, the team has deployed an array of optical and infrared sensors across multiple sites, all tuned to detect fast-moving objects entering Earth's upper atmosphere. Their objective is simple: watch for anything that might arrive in the weeks after perihelion, whether fragments, probes, or unexplained flashes. The project's software sifts through terabytes of data, flagging anything that deviates from the expected background of meteors and satellites. The weeks following perihelion are a test of readiness and patience. Every anomaly, every spike in brightness or radio noise prompts a flurry of cross-checks and rapid response observations. Scientists pore over raw data, comparing it against models for natural comet breakup and searching for patterns that might hint at something engineered. The sense of anticipation is matched by a determination to extract every possible clue from the encounter, regardless of the outcome. For many in the planetary science community, this is a rare chance to study materials from another star, a sample return mission delivered by nature itself. For others, it is a high-stakes watch for anything that could challenge assumptions about our place in the cosmos. Either way, the monitoring effort is relentless and global, a demonstration of what happens when science refuses to blink, even when the universe throws up its brightest glare. On July 1st, 2025, astronomers confirmed 3I/Atlas as only the third known interstellar object to enter our solar system. Unlike its predecessors, it is larger, potentially over 5 kilometers across, faster, and its arrival along the ecliptic plane defies statistical expectation. Spectroscopic data revealed a coma rich in carbon dioxide at distances where such activity is rare, and nickel vapor appeared before iron, contradicting established comet chemistry. Despite these anomalies, Atlas's decisive moment, its perihelion on October 29, 2025, remains hidden behind the Sun. No ground telescope can observe this event directly. Experts like Avi Loeb have called this the Trojan horse problem, urging caution in case the object is not purely natural. Yet mainstream missions see it as an unprecedented scientific opportunity. As of today, whether Atlas will behave like a comet or reveal something engineered remains unknown. What happens next will be determined by evidence, not assumption. The story is not finished. The data collected in the coming months will decide how we remember 3I/Atlas.